Hey everyone, and I am so excited to get into today's topic. But first, this information is presented by Bluewater Auto Restoration. Welcome back. This is week 18 of the 2026 Bluewater Auto Restoration podcast. We release new podcasts every Saturday morning. In this deep dive, we look at the NSU Max series, engineering the German motorcycling legend, and I want you to just imagine something with me for a second.
Oh, I love a good visualization.
Right. So imagine you are standing in a quiet garage and you're running your hand along the cool, kind of patinated steel of a beautifully preserved piece of 1958 history. You are looking at a motorcycle, but as you really study the way the metal frame is stamped and the way the engine is assembled without those usual exposed chains and crude gears, you realize this isn't just a machine. You are looking at an absolute masterclass in mid-century resilience and, frankly, pure engineering audacity.
Yeah, that is exactly the right word for it, audacity.
And capturing that exact feeling is what we do here. So our mission for this deep dive is pretty ambitious.
We have a lot of ground to cover today.
We really do. We are going to trace how a uniquely humble manufacturer, and I mean starting with literal knitting needles, if you can believe, that transformed into the largest motorcycle producer on the planet.
It's a wild trajectory.
It is. And we will tear down the brilliant mechanical architecture of the NSU Max platform, specifically the Maxi 175. And most importantly, we are going to dive deep into the laboratory, so to speak, to examine exactly how Bluewater Auto Restoration is actively, painstakingly preserving this legacy today without erasing its history.
Which is such a vital distinction in the restoration world.
Exactly. Okay, let's unpack this. Because to understand the motorcycle sitting on the BWAR lift right now in 2026, we really have to look at the industrial DNA forged way back in 1873.
Right, and if we connect this to the bigger picture, Heinrich Stoll and Christian Schmidt established that DNA in a small metal shop in Riedlingen, Germany. And, they weren't dreaming of combustion engines or Bonneville land speed records.
Oh, not at all.
Not even close. They founded a mechanical shop for manufacturing knitting machines.
I always find that transition so jarring. It feels absurd on its face, right? Like, how does a company go from knitting sweaters to building internal combustion legends?
It sounds like a punchline.
It really does. But mechanically, the leap isn't actually that wide, is it?
No, mechanically, it is practically a straight line. I mean, consider the anatomy of a 19th century industrial knitting machine.
Okay.
You are dealing with hundreds of microscopic steel needles, interlocking cams, high-speed actuating levers. The synchronization has to be absolute.
Because if it's off, even a little bit...
Exactly. If a single cam profile is machined incorrectly, or if a lever's tolerance is off by a fraction of a millimeter, the thread snaps, the machine binds, and the entire production line just stops.
Wow. So they were basically running a masterclass in precision metallurgy decades before anyone even conceptualized a modern engine block.
Precisely. And they moved the operation to Neckarsulm in 1880, which, as a fun geographic footnote, is where the acronym NSU comes from.
Oh, wait, really? I didn't know that.
Yeah, it's the union of the rivers Neckar and Solm, NSU.
Okay, that makes so much sense.
Right. So by setting up there, they cultivated a workforce that was intimately familiar with casting, milling, and assembling interlocking metal components that had to run flawlessly under constant friction for hours on end.
They were like inadvertently training an automotive workforce.
Without even knowing it,
Yeah.
which really explains their hard pivot in 1886.
Right, the bicycle craze.
Yes, the safety bicycle hits the European market. This is the modern design we know today. 2 equal-size wheels, a chain drive replacing those old dangerous penny farthings.
Those giant front wheels.
Exactly. So demand goes through the roof. And NSU looks at their knitting machine tooling and realizes, hey, we are perfectly positioned to mill bottom brackets, wheel hubs, chain rings.
Because it's all just precision circular metal work.
Exactly. And they pivot so aggressively that by 1892, they completely abandon the knitting machines. Their founding product just gone.
That is wild. But I guess that adaptability becomes their defining corporate trait going forward.
It absolutely does. But it's their reputation for that metallurgical precision that pulls them into what I call the automotive shadow history.
Oh, I love this part.
It's so fascinating.
Yeah.
By the late 1880s, Gottlieb Daimler is trying to construct his first true four-wheeled automobile.
Right, the pioneer of the car.
But prior to this, inventors were just bolting heavy engines to wooden horse carriages.
Which I imagine didn't go well.
No, they literally vibrated themselves to pieces.
Yeah.
Wood can't handle that harmonic resonance. Daimler needed a purpose-built, structurally rigid, lightweight metal chassis.
Mm.
And he didn't have the capability to manufacture it in-house.
So where does he go?
He went to NSU.
I still cannot get over that fact. I mean, you watch any mainstream documentary on automotive history, and it is entirely focused on Daimler and Benz tinkering in their isolated workshop.
The lone genius myth, yeah.
Exactly. Yet NSU fabricated the bones of the very first Daimler automobile. It's like finding out, I don't know, that Rolex secretly built the prototype for the Apollo moonlander.
That is a very apt comparison.
Right. Because they weren't an aerospace company, but they understood microscopic precision better than anyone else.
Yeah, because a combustion engine in 1888 produced horrific, unbalanced harmonic vibrations. NSU had the engineering foresight to understand torsional rigidity and how to construct a frame that wouldn't shear its rivets under that stress.
Just incredible.
And their shadow involvement didn't stop there. Jump forward a bit to 1934. Ferdinand Porsche is conceptualizing the people's car, and he needs a running prototype to prove the concept to investors and the government.
The VW Beetle, essentially.
Okay. Yes, the direct ancestor. He contracts NSU to build a prototype Porsche Type 32.
The most mass-produced car platform in history, and NSU quietly hammered out the prototype.
Right in their Neckarsulm factory.
They were the silent architects behind the scenes, all while building their own empire at the same time. I mean, they opened Germany's first dedicated motorcycle plant in 1900. They put out their first motorized two-wheeler in 1901. And by 1927, they were the first German manufacturer to implement a moving assembly line for automobiles.
They scaled into an absolute industrial titan. I mean, during the 1930s, their lightweight commuter motorcycle, the Quick, moved over 240,000 units.
That is a staggering number for the 1930s.
It really is. They possessed the most advanced manufacturing infrastructure in Central Europe, which, historically speaking, made them an unavoidable asset when global conflict erupted.
Right. Moving into the 1940s, the entire facility was requisitioned for wartime production.
Yes, they were tasked with developing and manufacturing the Kettenkrad.
Oh, the Kettenkrad. What a weird, fascinating machine.
It's so strange. It was a highly specialized half-track vehicle designed for the extreme mud and snow of the Eastern Front.
Right.
It utilized the front wheel and steering geometry of a motorcycle, made into a rear hull driven by tank treads.
Okay, from a purely mechanical standpoint, I have to ask, how does a standard motorcycle front wheel actually steer a tracked vehicle? I mean, in thick mud, wouldn't the tracks just push the front wheel sideways? It seems like it would just plow straight.
You would think so, yeah. But it is a brilliant piece of differential gearing.
Oh, really?
Yeah. For shallow turns, the rider turned the handlebars and the front wheel guided the vehicle naturally. But if the rider turned the bars past a certain degree, a linkage automatically engaged a steering brake on the inner track.
Ah, I see.
So this slowed the inside track while transferring power to the outside track, pivoting the entire vehicle like a tank. It required a highly sophisticated transmission and final drive to operate reliably in sub-zero mud.
That is genius. But, of course, manufacturing that sophisticated military hardware turned the Neckarsulm plant into a primary strategic target.
Unavoidably.
Right. So in 1945, literally weeks before the conflict in Europe ended, Allied bombing raids decimated the facility.
It was almost entirely leveled.
The infrastructure that birthed the Daimler chassis and the Porsche prototype was just reduced to twisted steel and shattered concrete.
The post-war reality was incredibly bleak. I mean, the German infrastructure was entirely shattered, supply chains were non-existent, and raw materials were heavily rationed.
People were just trying to survive.
Exactly. Yet the surviving workers simply walked back into the rubble in 1946. They initially repurposed the surviving machine tools to repair damaged Allied vehicles.
Just to keep the lights on, so to speak.
Right. Scavenging parts, melting down whatever scrap aluminum from downed aircraft or broken vehicles they could find. And astoundingly, within that same year, they pieced together enough tooling to resume production of the pre-war 98cc Quick.
Which really speaks to the absolute desperation of the market. The economic landscape of the late 1940s wasn't about leisure.
No, nobody was buying a motorcycle for a Sunday cruise.
Right. The roads were destroyed, fuel was incredibly scarce, and capital was non-existent. People needed survival mobility.
That's a great term for it.
They needed a machine that could navigate cratered roads, haul a sack of potatoes, get them to a factory job across the city, and run on terrible quality fuel without seizing up.
And NSU read the economic terrain perfectly. They didn't try to build luxury cruisers. They focused entirely on hyper-efficient, small-displacement utility.
Makes total sense.
This really initiates their golden era. They launched the 100cc Fox in 1948, the Lux 200 in 1950, and the quickly Moped, which eventually shattered sales records, moving over 1 million units.
A million units. Just staggering. And the engineering was heavily supported by an absolute masterclass in marketing, right?
Arguably the best in the business at the time.
Arthur Westrop headed their advertising department, and he understood the psychology of a recovering, exhausted populace so well. He didn't sell them on technical specs like compression ratios or valve timing. He sold them on relief.
Yes.
He crafted these punchy, rhyming slogans. For the Fox, it was Fix Fahrer, fahren Fox, smart riders ride the Fox.
And for the quickly Moped, his copy was even more pragmatic, right? Nicht mehr laufen, quickly kaufen, no more walking, buy a quickly.
It's brilliant.
It addressed the literal physical exhaustion of the consumer. You're tired, buy this.
And for the Lux 200, wer Lux fährt, der kann lachen. Who rides the Lux can laugh. I actually think the styling of the Super Lux variant is highly indicative of that psychological shift, too.
Yeah.
Well, in the early 1950s, the visual landscape of Germany was incredibly drab. It was all concrete dust, military surplus drab, and gray wool. But NSU offered the Super Lux in vibrant jade green, rich blue, and gloss black.
Bringing color back.
Exactly. Imagine the contrast of a gleaming jade green motorcycle with polished aluminum engine cases rolling down a war-torn gray street. It was a visual indicator that the economy was finally stabilizing. It was hope in physical form.
That's a profound way to look at it.
Yeah.
And Westrop's crowning marketing achievement, however, was for their flagship line. Mit Motorrad meant Man Max.
By motorcycle, Max is meant.
Yes, it was an audacious linguistic claim, essentially stated that NSU owned the very definition of the word motorcycle. But that arrogance was entirely backed by the engineering department.
Okay, let's address the strategic paradox here, though. Because their entire corporate identity, backed by Westrop's marketing, is focused on cheap, reliable commuting for the working class. Yet, simultaneously, NSU is pouring millions of marks into international Grand Prix racing and land speed records. If your target demographic is a baker needing a 100cc moped to deliver bread, why are you funding a factory racing team to go 210 miles per hour on an American salt flat?
It's a fair question, but it comes down to two foundational pillars of automotive manufacturing. Trickle-down metallurgy and the halo effect.
Okay, let's break those down.
Sure. So in the 1950s, the 125cc and 250cc Grand Prix classes were the most fiercely contested engineering battlegrounds on Earth.
Because to make a tiny engine win a world championship, you have to push the physical limits of combustion.
Exactly. When you are forcing a tiny 250cc engine to rev past 10,000 RPMs for hours on end, you encounter catastrophic failures.
Parts just break.
Violently. Valves float, connecting rods stretch, pistons melt, and the oil just turns to froth. By funding a racing program, NSU essentially created a high-speed torture testing laboratory.
Oh, I see.
The aluminum alloys developed to keep a race piston from detonating under immense thermal load are the exact same alloys that make a commuter bike run for 50,000 miles without a rebuild.
It's durability through extremity. And the halo effect provides the psychological return on investment, right?
Yes.
The old phrase, win on Sunday, sell on Monday, totally applies here. If I'm buying that little Fox 100 to get to the factory, seeing the NSU badge on my tank reminds me that the same company just conquered the globe on the racetrack.
And conquer they did. Werner Haas took the 250cc World Championship in 1953 and 1954 on the factory Renmax.
The Renmax was incredible.
An absolute marvel. A twin-cylinder machine that showcased NSU's mastery of high RPM thermodynamics. But even more telling was H.P. Muller's 1955 World Championship.
Right, because he wasn't even on a factory bike.
No, he didn't ride a factory prototype. He rode a Sportmax as a privateer. He purchased the machine, maintained it himself, and beat the fully funded factory teams of rival manufacturers.
There is literally no better proof of concept than a private citizen buying your product off the shelf and using it to beat the world's best.
It's the ultimate endorsement.
But track racing wasn't enough to satisfy their engineering ego, was it? They needed absolute, unadulterated terminal velocity.
They did.
So they shipped their engineers across the world to the Bonneville Salt Flats in Utah.
Bonneville is the ultimate crucible for an engine.
Because of the conditions?
Yes. The altitude starves the engine of oxygen, the ambient heat is brutal, and the salt surface offers incredibly tricky traction. Yet the flat, endless expanse allows for aerodynamic testing that's impossible anywhere else.
Right.
So in 1951, NSU arrived with a 500cc supercharged machine and clocked 180 miles per hour.
Which is absolutely terrifying on 1950s bias-ply tires. I can't even imagine the speed wobble.
It takes a special kind of bravery. But they returned in 1956 with a streamliner, a fully enclosed, aerodynamically perfect silver shell piloted by Wilhelm Hertz.
Like a rocket on wheels.
Exactly. They packed it with a highly tuned, mechanically supercharged 500cc engine and hit 210 miles per hour.
210 miles per hour.
To achieve 210 miles per hour on two wheels in 1956 requires an unparalleled understanding of aerodynamic drag coefficients, forced induction, and high-speed chassis stability.
Incredible.
Wilhelm Hertz was incredibly brave, yes, but the engineering statement from NSU was definitive. Nobody on Earth understands the physics of a motorcycle better than we do.
And all of that R&D, the metallurgy from the Grand Prix circuits, the aerodynamics from Bonneville, all of it was channeled directly into the brain of their chief designer, Albert Roeder.
Albert Roeder was a genius.
He took the racing DNA and translated it into consumer reality, birthing the Max platform.
The Max series is, without a doubt, the absolute zenith of 1950s motorcycling.
Let's talk specs.
Introduced in 1952 as the Type 251 OSB, it featured a 247cc four-stroke single producing around 17 horsepower. It utilized a central rear spring for its suspension and could comfortably cruise at 126 kilometers per hour.
And they iterated quickly, too, didn't they?
Very quickly. The 1954 Special Max introduced full-width alloy drum brakes, dramatically reducing brake fade under heavy load.
Which is vital when you're cruising at those speeds.
Exactly. And by 1956, the Supermax arrived, bumping output to 18 horsepower and replacing the single central spring with twin external rear shocks.
Modernizing the suspension.
Yes, which vastly improved the damping characteristics and cornering stability. They even produced a Scrambler variant in 1958, exclusively for the U.S. market, featuring high-swept exhaust pipes for off-road clearance.
But regardless of the variant, the Max platform was really defined by two revolutionary engineering departures.
Yes, two massive innovations.
First was the chassis construction. The industry standard at the time was to braze or weld tubular steel together to form a frame, right? Just bending pipes.
That was a cheap, easy way to do it.
But Roeder discarded that entirely. He utilized a pressed steel monocoque frame. Let's break down why that matters. Tubular frames are relatively cheap to produce, but Roeder opted to use massive hydraulic presses to stamp flat sheets of steel into complex three-dimensional halves, which were then seam-welded down the center. Why absorb that massive tooling cost up front?
Well, because the engineering benefits are manifold. Once the expensive tooling is in place, stamping is highly efficient for mass production.
Right.
More importantly, a pressed steel monocoque acts as a stressed skin. It offers immense torsional rigidity compared to mild steel tubes.
So it handles better.
Exactly. When you lean the motorcycle into a hard corner, the frame doesn't flex or hinge, keeping the wheels perfectly aligned.
It tracks straight and true.
Furthermore, the hollow interior of the stamped frame allows the wiring harness and cables to be routed internally, resulting in a remarkably clean, streamlined aesthetic.
No messy wires zip-tied everywhere. The frame is brilliant, but we have to talk about Roeder's absolute masterpiece, the valvetrain. Let's dig into the Ultramax overhead camshaft system.
Oh, this is the best part.
It really is. So, in a standard engine of that era, the crankshaft is spinning at the bottom, and the valves sit at the top. You have to connect them somehow so the valves open in perfect synchronization with the piston stroke. The conventional methods were push rods, chain-driven cams, or bevel gears.
Right. And all of those have major drawbacks.
What's fascinated me here is how Roeder evaluated those compromises. Push rods limit your RPM ceiling because the massive weight of the metal rods causes valve float at high speeds, right?
Yes, the valves literally can't close fast enough.
And chains stretch over time, throwing off the engine timing and causing choke whip. Bevel gears, on the other hand, are incredibly expensive to machine perfectly and produce a horrific whining noise.
So Roeder evaluated these compromises and invented an entirely new mechanical pathway.
He used a system of reciprocating rods, and my favorite way to picture this is to think of a classic steam locomotive.
Okay, I like this analogy.
Picture the massive steel side rods on a steam train that connect the driving wheels. As one wheel turns, the rod pushes and pulls the next wheel in perfect harmony. Roeder took that exact concept, miniaturized it, and placed two solid steel rods inside the engine block. They connected an eccentric cam on the bottom crankshaft to an eccentric cam on the top cylinder head.
What's fascinating here is how phenomenal a solution it is mechanically. As the crankshaft spins, These two rods reciprocate up and down thousands of times a minute.
Just a blur of motion.
Yes. But because they are solid steel, there is zero stretch.
Unlike a chain.
Exactly. The timing between the crank and the cam remains absolute, regardless of thermal expansion or RPM load.
But the physical forces on those rods must be staggering, right? They are rapidly alternating between tension and compression at like 6,000 RPM.
They are. And that is exactly where the trickle-down metallurgy from the racing program paid off. NSU knew exactly how to forge and temper those rods to prevent them from snapping under harmonic vibration.
It all comes together.
It does. By eliminating chains and gears, Rotor created an engine that was phenomenally quiet, incredibly smooth, and largely maintenance-free.
You never had to adjust a cam chain tensioner because there just wasn't one.
Exactly. It was over-engineered for ultimate longevity.
Which brings us to the core of our deep dive today, and really the specific focus of the Bluewater Auto Restoration Project, the NSU Maxi.
The Maxi.
Yes, because NSU realized this Ultramax architecture was just too brilliant to reserve only for their premium 250cc line. So around 1957, they scaled it down to create the Maxi 175, aiming directly at the everyday commuter.
The Maxi often lives in the shadow of the Supermax, but I argue it is the purest distillation of NSU's philosophy.
Why is that?
Well, the 175cc displacement was highly strategic. In post-war Europe, vehicle taxation and insurance premiums were strictly tiered by engine size. A 175cc engine fell into a highly favorable tax bracket, making it significantly cheaper to operate than a 250cc.
Okay, so it saved the rider money.
Exactly. Yet it provided vastly more passing power and highway capability than a 100cc or 125cc machine. These are the perfect sweet spot.
Let's look at the engine geometry of the Maxi for a second. It utilized a bore of roughly 62 millimeters and a stroke of 58 millimeters. So it's an over-square design.
Yes, it is.
For the uninitiated listener, why wouldn't they just make it a perfectly square 60 by 60? What does that slightly larger 62 millimeter bore actually achieve?
That's a great question. An over-square design where the cylinder bore is wider than the piston stroke is long allows for larger valves in the cylinder head.
Because there's physically more room across the top of the cylinder.
Precisely. And larger valves mean the engine can breathe better, drawing in more fuel and air at higher RPMs.
So it makes more power up top.
Right. It sacrifices a tiny bit of low-end tractor torque, but it allows the 175cc engine to rev freely and produce a highly respectable 12.5 horsepower.
And it fed that air and fuel through a really high-quality Bing slide carburetor.
The Bing carbs were excellent.
They were. The needle tapers and venturi design on those Bings were incredibly precise, providing excellent fuel atomization. This allowed the Maxi to hit top speeds of 80 to 100 kilometers per hour, but the efficiency is what truly staggers me.
It was incredibly frugal.
It consumed roughly 2.5 to 3.0 liters of fuel per 100 kilometers. In American metrics, that is between 78 and 94 miles per gallon.
For 1958, that is an engineering triumph.
It really is.
And that efficiency is a direct result of the reduced internal friction from the Ultramax rod system, the precise fuel metering of the Bing carburetor, and the overall lightweight monocoque chassis we talked about.
It's all those incremental gains adding up. But the engineering surprises didn't stop there. The Maxi utilized a dry sump lubrication system.
Which is wild for a 175cc commuter.
Right. You typically only find dry sumps on high-end sports cars like Porsches or dedicated race machines.
Exactly.
In a standard wet sump, the oil just sits in a pan at the bottom of the engine, and the crank basically splashes through it. But in a dry sump, the oil is stored in a completely separate tank.
Right. A pressure pump forces oil directly into the crank and valvetrain, while a secondary scavenge pump violently sucks the hot oil back out of the engine block and returns it to the tank.
Why go through all that complexity and added weight of 2 pumps on a commuter bike?
Because a dry sump system ensures constant pressurized lubrication regardless of the bike's angle during cornering or hard braking.
So no oil starvation.
None. Furthermore, keeping the bulk of the oil in a separate tank acts as a heat sink, significantly lowering the overall engine temperature.
Huh. I didn't think about the cooling aspect.
It's crucial. This prevents the oil from shearing and breaking down under the thermal load of long highway commutes. Again, massive over-engineering for a utilitarian machine.
And my absolute favorite feature, the fully enclosed chain drive.
It's so practical.
Think about riding a motorcycle in Munich in, say, November of 1958. You're wearing your nice wool work trousers. A standard exposed drive chain is constantly slinging black, sticky gear oil onto your left leg.
Ruining your clothes.
Exactly. Furthermore, every time it rains, the front tire kicks up silica sand and road grit directly onto the chain, turning that sticky oil into a highly abrasive grinding paste.
Which destroys the sprockets in a few thousand miles.
Right. But NSU engineered a brilliant solution out of pure respect for the rider. They completely encased the final drive chain in a beautifully stamped metal housing.
Inside this housing, the chain ran through a continuous oil bath.
And the casing even featured rubber gaiters to allow the suspension to move up and down without breaking the seal.
The result, not a drop of oil touches your trousers, and not a single grain of sand touches the chain.
A chain that might survive 5,000 miles exposed to the elements could easily last 30,000 miles inside that sealed oil bath. It is purely rider-centric engineering.
And that profound durability is exactly why surviving examples of the Maxi 175 still exist today, and why Bluewater Auto Restoration initiated a comprehensive preservation project on a late 1950s, approximately 1958 model in March of 2026.
This is where we need to dive deep into the BWAR methodology. We mentioned at the start that they're focusing on authenticity and preservation.
Which is so important.
It is, because the restoration community often falls into the trap of over-restoration. Somebody finds a vintage bike, sandblasts the entire frame down to bare metal, dips it in a modern 2-part epoxy primer, and shoots it with a modern high-gloss urethane clear coat.
Making it look shinier than it ever did.
Exactly. Then they take the aluminum engine cases to a buffing wheel and polish them until they look like chrome mirrors.
The problem with that approach is that it actively destroys the historical record.
It erases it.
Exactly. An NSU rolling off the Neckarsulm line in 1958 did not have a mirror-polished engine block. It had the distinct, slightly rough texture of a sand-cast aluminum mold.
You could see how it was made.
Right. It had visible casting flash marks where the molds met. The factory paint was likely a single-stage nitrocellulose or synthetic enamel, which has a very specific depth and luster. It does not look like a modern, plasticized clear coat.
When you over-restore, you turn a piece of industrial history into a shiny plastic toy. You erase the evidence of the human hands that actually built it. BWAR's approach is radically different, right?
Completely different.
Their 1958 Maxi 175 is a largely unmolested survivor. So what is their step-by-step methodology to preserve it?
Well, it begins with chemical stabilization rather than abrasive stripping. For the pressed steel frame, BWAR utilizes specialized penetrating oils and highly localized microabrasion techniques.
Okay, what does that achieve?
Their goal is to gently remove active, flaking rust while carefully preserving the underlying dark, stabilized oxide layer, the patina. They want to seal and protect the surviving original paint, not bury it under modern chemicals.
And what about the hardware, the nuts and bolts? The easy route is to just throw all the original fasteners in the trash and buy a bucket of shiny, modern stainless steel bolts.
BWAR absolutely refuses to do that. NSU utilized specific hardware with period-correct cadmium or zinc plating. BWAR assesses every individual fastener.
Every single one.
Every single one. If a bolt has surface oxidation but retains its structural integrity, they will painstakingly clean the threads, neutralize the oxidation chemically, and reuse the original factory fastener.
That is dedication.
They're preserving the exact tensile strength and metallurgy that Albert Roeder specified.
The mechanical rebuild is equally meticulous, especially concerning that dry sump lubrication system we discussed. After 70 years, the tolerances inside those mechanical scavenge pumps can wear down.
And rebuilding a 1950s dry sump pump requires absolute precision. If the gear teeth inside the pump wear down even a fraction of a millimeter, the pump loses its ability to scavenge hot oil efficiently.
Which leads to engine overheating and failure.
Exactly. So BWAR's technicians measure these internal tolerances with micrometers. If a component is out of spec, they don't simply retrofit a modern electric pump. They machine the original housings or source period correct new old stock replacement gears to ensure the mechanical heart of the Ultramax engine functions exactly as designed in 1958.
Because the ultimate objective is that when a mechanic or an enthusiast looks at this Maxi 175 after BWAR completes the project, they aren't looking at a modern reinterpretation.
No, they are viewing a perfectly preserved snapshot of peak German engineering.
And 1955 through 1958 truly was the absolute peak. I mean, they were moving 350,000 units annually. They held the Bonneville land speed records. They were the undisputed kings of global two-wheeled mobility.
This raises an important question, though, which makes their sudden collapse one of the most fascinating case studies in industrial history.
It was so fast.
Within a decade of that peak, the motorcycle division effectively evaporated. In 1964, the last NSU scooters rolled off the assembly line. By 1965, motorcycle production ceased entirely, concluding with a small run of the Quick 50 model.
The company that famously claimed buy motorcycle Max's meant completely abandoned the motorcycle market.
Just
Just
walked away.
was it a failure of engineering? Like, did the Ultramax system suddenly become obsolete or unreliable?
Not at all. The engineering remained spectacular. The failure, if you can even call it that, was macroeconomic.
What changed?
Germany and the broader European market entered the Wirtschaftswunder, the profound post-war economic miracle.
The standard of living skyrocketed.
Exactly. Consider our hypothetical Munich worker who bought a Maxi 175 in 1958 out of sheer necessity. By 1963, his wages had increased dramatically.
He had money in his pocket.
He now possessed disposable income. He no longer wanted to ride through the sleet in November in a wool coat. He wanted a steel roof over his head. He wanted a heater. He wanted 4 wheels.
The market violently transitioned from demanding economical two-wheeled transport out of desperation to demanding automobiles out of newfound prosperity.
And NSU, true to the corporate DNA that saw them ruthlessly drop knitting machines for bicycles 80 years prior, read the writing on the wall.
They just pivoted again.
They shuttered the motorcycle division and pivoted aggressively back to automobiles. They launched the compact NSU Prince line.
And Arthur Westrup's marketing team didn't miss a beat, did they? They rolled out the new slogan, Mit NSU, Prince bist du König. With NSU Prince, you are king.
They were so good at tapping into the consumer mindset.
But they weren't content just building conventional, piston-driven economy cars, were they? The engineering arrogance that led Albert Rotor to invent the Ultramax reciprocating rod system was still deeply embedded in the company culture.
Oh, very much so. In 1957, they partnered with an engineer named Felix Wankel to pioneer the rotary engine.
Ah, the infamous Wankel rotary.
The Wankel engine is perhaps the ultimate expression of NSU's engineering ethos. Absolutely brilliant, highly unconventional, and immensely difficult to execute flawlessly.
How does it work compared to a normal engine?
Well, Wankel sought to eliminate the reciprocating mass of pistons entirely. Instead of pistons moving up and down, stopping and reversing direction thousands of times a minute, which causes vibration, the Wankel engine utilized a triangular rotor spinning continuously inside an epitrochoid or oval-shaped housing.
It is mechanically poetic, honestly. In the 1950s, they said, chains and gears are terrible. Let's use spinning eccentric rods. In the 1960s, they said, pistons are terrible. Let's use a spinning triangle.
It's outside-the-box thinking at its finest.
It allowed for an engine that was incredibly compact, exceptionally smooth, and capable of astronomical RPMs. But it was a massive gamble.
A gamble that fundamentally strained the company to its breaking point.
Why? What went wrong?
The physics of the rotary engine present a severe challenge regarding the apex seals.
What are those?
These are the tiny metal blades at the 3 tips of the triangular rotor. They must maintain a perfect airtight seal against the combustion chamber wall as the rotor spins at high speed.
Why are those seals so problematic?
Because of thermal dynamics. In a traditional piston cylinder, the entire metal ring expands and contracts relatively uniformly. But in a rotary engine, combustion happens in only one specific zone of the oval housing.
Oh, so one side gets way hotter.
Exactly. That means one side of the engine is significantly hotter than the other. This uneven thermal expansion causes the apex seals to scrape unevenly against the housing.
That sounds bad.
In the early NSU rotary engines, this caused chatter marks. They actually referred to them as the devil's scratch marks on the interior walls.
And once you scratch the housing, you lose combustion compression, the engine loses power, and I assume it begins burning massive amounts of oil.
Precisely. The warranty claims on the early rotary-powered cars, like the revolutionary NSU Row 80, were astronomically expensive.
It bled them dry.
The financial hemorrhage from developing and fixing this bleeding-edge technology, compounded by the rapidly shifting automotive market, forced NSU to seek a corporate lifeline.
Which arrived in 1969 when NSU was forced to merge with Auto Union, a conglomerate that had recently been acquired by Volkswagen.
The merger created a new entity, Audi NSU Auto Union AG.
That is quite the mouthful.
Over time, that mouthful of a corporate title was streamlined, and the NSU name was quietly dropped from the branding entirely. They became simply Audi.
But the physical legacy remains, doesn't it?
It absolutely does. The sprawling NSU plant in Neckarsulm is currently one of Audi's most vital and technologically advanced manufacturing facilities. If you walk the perimeter of the factory today, the surrounding streets are still named NSU Strasse and Auto Union Strasse.
That is just incredible, and it provides an incredibly profound context for what Blue Water Auto Restoration is doing right now.
It really frames the importance of the work.
When we look at that 1958 Maxi 175 on the lift, we aren't just looking at a 12.5 horsepower vintage commuter. We are examining a physical timestamp. We are looking at the metallurgical DNA of a company that forged the Daimler chassis, survived the total eradication of World War II, shattered speed records at Bonneville, pioneered the rotary engine, and ultimately sacrificed its own name to build the foundation of the modern luxury powerhouse that is Audi.
Maxi 175 represents a fleeting, perfect moment of absolute engineering supremacy, preserved in the silent, precise mechanical movements of the Ultramax valvetrain.
It is an incredible story of survival and innovation, and I highly encourage you, our listeners, to follow along as this history is painstakingly preserved. Make sure you visit the BlueWater.CA website to see the detailed progress, the chemical preservation, and the mechanical teardown of this exact 1958 NSU Maxi 175 project.
It is definitely worth looking at.
Seeing the photos of Albert Roeder's rod-driven valvetrain being carefully revived is absolutely fascinating. And as a quick reminder, our podcasts are available on Spotify, YouTube, Apple Podcast, or SoundCloud.
As we conclude this deep dive, I want to leave you with one final thought regarding corporate evolution.
Let's hear it.
We've spent this hour analyzing a company that survived for nearly a century by ruthlessly shedding its past. They abandoned knitting machines for bicycles, bicycles for world champion motorcycles, and motorcycles for rotary engine cars the absolute second the market demanded it.
No hesitation.
They survived by repeatedly erasing their own identity to invent the future. So look at the massive, seemingly invincible corporate giants of our modern era, the ubiquitous tech conglomerates and automotive titans. Which of them possesses the organizational courage to completely abandon their defining product to survive the next 50 years? And which ones are too anchored to their past to avoid being left behind in the rubble?
Wow, a phenomenal question to chew on. Thank you for joining us on this deep dive into industrial history. We'll see you next Saturday.